Today we're talking about rate of change. You've heard about rate of change in the past, but usually we've talked about it as slope. We've always learned slope or talked about slope from linear functions or straight lines before, but what about slopes of exponential functions or of any other type of nonlinear line? Before we get too deep into this topic, there are some definitions for you to know. This triangle is read as the word delta. Delta y means change in y. And since y is our vertical axis, we've always called it rise. Delta x means change in x. And since x is our horizontal axis, we've always called it run. So now we have different ways to talk about slope. We can define it as rise over run, delta y over delta x, or change in y over change in x. And it's all the same value. With linear functions, slope was very easy to find. From one point on the grid to the next, we would always look at the rise and the run and get our slopes from those values. For instance, this one went from one point to the next, we went up 2 and to the right 3, so we got a slope of 2/3. If we didn't have a graph, we used the slope formula. y2 minus y1 would give us the change in y over x2 minus x1 for the change in x. When we were given 2 points on a line, but not the line itself, we could plug those values into our slope formula and still find our slope. But now we're not dealing with linear functions anymore. Here's the graph of an exponential function. Why do you think the slope will not be as straightforward this time? Well, if you take a look at this section of graph, it has a very small slope. It's increasing very slowly. But all of a sudden, we start to increase faster and faster. So this section of graph, for instance, will not be the same slope as this first section of graph. So since our graph itself is not constant, the slope for one part of the graph will not be the same as the slope for a different part of graph. Because the slopes are not as straightforward, we need to introduce a new concept called the secant line. A secant line is a line connecting 2 points on a curve that will make it easy for us to find the average rate of change for that section of graph. Let me show you what I mean. Here we have the graph of the exponential function y equals 2 to the x power. And we've put 2 points on that graph, point A where x is 0 and point B where x is 3. So we're looking at an interval from 0 to 3. If I draw a line through points A and B, that becomes a secant line. And it's very simple for me to find the slope for the green secant line. From point A to point B, we go up 7 units and to the right 3 units, giving us a slope of 7/3. But what if I was talking about a different set of points? What if I added a third point, point C, and drew a secant line through points A and C? And since C is where x is 2, we're talking about the interval from 0 to 2. From points A to C, we go up 3 units and to the right 2, so our blue line has a slope of 3/2. Let's try a third secant line going through points C and B. That's from where x is 2 to where x is 3, so we're talking about the interval from 2 to 3. From point C to point B, we go up 4 units and to the right 1 unit, so I get a slope of 4. And just within that small section of graph, I found 3 completely different slopes. So just to kind of pull all of that together, the slopes are not the same, and the interval we chose made the difference. And yes, we can assume that the same thing is going to happen for any nonlinear graph. Now, just like finding slope without a graph was not quite as straightforward and we had to have a formula, if we don't have a graph to find the rate of change or to find the average rate of change, we also require a formula. If we're just given the function, we are going to use this new formula to find average rate of change over an interval. Delta y over delta x, or change in y over change in x, is defined as f of b minus f of a all over b minus a. And we're going to get the values a and b from the interval we chose. Remember, intervals only contain x values. So a is going to be the x value from our first point, and b is going to be the x value from our second point. F of b comes from evaluating our function at b, and f of a is going to come from evaluating our function at a. Let's see if we can clarify this. We're going to try to find some average rates of change for the function x squared minus 4. And we're going to find the rate of change across 4 different intervals from the same function. Let's start with the interval from -5 to -2. First of all, we need to define a and b. It doesn't matter really which value you choose as a and which value you choose as b. We just need to keep them straight. Taking those values and plugging them into our rate of change formula, we're going to have f of b, in this case f of -2, my function at -2, minus f of -5, my function at -5, all over b minus a, or -2 subtracting -5. Just taking those a and b values and putting them in our formula. To evaluate this, I need to evaluate my function at -2 and again at -5, so let's take care of that first. F of -2 means to take -2 and substitute it into our original function for x. So when I do that, I get -2 to the second power minus 4. -2 times itself gives me +4, and when I subtract 4, I get 0. Let's do the same thing for -5. -5 to the second power is 25. Minus 4 leaves us with 21. And now I have all the values I need. Taking the 0 and 21 and replacing the f of -2 and f of -5 is going to look like 0 minus 21 over -2, subtracting a negative becomes an addition, 5. Simplifying further, that gives us -21 over 3, which reduces to -7. -7 is our average rate of change over the interval from -5 to -2. Let's try that again. This time, let's find the average rate of change from 0 to 4. Again, I need to define which one is A and which one is B, and put them in my formula. Just a word of caution, see how the 2 4s are together and the 2 0s are together? That will always need to be the case to give you the right rate of change. Now I need to evaluate my function at 4, and evaluate my function at 0. Let's start with f of 4. 4 to the second power minus 4 gives me 16 minus 4, and we end up with 12. F of 0, 0 squared is 0, minus 4 leaves us with negative 4. Then I can take 12 and negative 4 and put them in my formula. 12 minus negative 4 over 4 minus 0 simplifies to 16 over 4, which reduces to 4. 4 is our average rate of change over the interval from 0 to 4. This time we want to use the interval from 5 to 8. So we need to find f of 8 and f of 5. F of 8 gives me 64 minus 4, which is 60. F of 5 is 25 minus 4, which gives us 21. Putting them in my formula, I get 60 minus 21 over 8 minus 5, which is 39 over 3, and that reduces to 13. Let's try one more, but I want to show you how to simplify the process even more. When I have a very simple function like x squared minus 4, I don't necessarily have to write out my function evaluations. If I'm going to plug in negative 3, I get negative 3 to the second power is 9, minus 4, I know that f of negative 3 is going to be 5. When I need to find f of 0, 0 squared is 0 minus 4, leaves me with negative 4. F of 0 is negative 4. So if you can do that part a little more simply, feel free. F of 0 was negative 4, f of negative 3 was 5, over 0 minus negative 3. When I simplify that, I'm going to get negative 9 over 3, and that's going to reduce to negative 3. Now that I have all 4 rates of change, remember that those are 4 different slopes basically across the exact same function, just based on the different intervals. So last thing we're going to do today is take a look at the actual graph. This is the graph of x squared minus 4. Can you see the different rates of change? Well, it's going to probably be helpful if we have them on the same page. Let's take a look at the interval from negative 5 to negative 2. That's this section of graph. Can you see kind of that the average slope is going to be negative 7? That's a pretty steep decrease. From 0 to 4, from where x is 0 to where x is 4, that's going to be this section of graph. The average slope here was 4. So we have an increase. We go up 4 units for every 1 unit we go across. From 5 to 8, from where x is 5 to where x is 8, that's going to be off our page here, but that has an average rate of change of 13. That's going to be a hugely steep incline. And from negative 3 to 0, from where x is negative 3 to where x is 0, that's this section of graph, and it has an average rate of change of negative 3. 4 different rates of change, 4 different slopes across the exact same function depending on which interval we chose. I think that's enough for today. I hope you have a fantastic day. Remember, you can review or rewind and review examples again. And I'll see you next time.